Let's talk a little bit more generally now about nuclear reactions. Here's an example. Here's a nuclear reaction where a helium with four nucleons, helium-4 can combine with nitrogen-14, and then they change into oxygen-17 and hydrogen, regular hydrogen. So two nuclei in and two nuclei out. We've talked about nuclear reactions a little bit so far, right? But only spontaneous radioactive decay of unstable nuclei that give off alpha, beta, gamma. So those are nuclear reactions that occur spontaneously and release energy, but uh, they aren't the only possible nuclear reaction. So here's one where two nuclei to start out with, and then two other ones to end up with. So in this case, you can see, well, of course, in all reactions, in all processes, that the conservation laws are obeyed. And so that includes charge. There's a charge conservation law. And you can see that right here in the equation, because I wrote this with the symbols, like, so the helium has subscript 2 on the left and superscript 4 on the right. Right? And that subscript 2 is the atomic number, or the number of protons, or the number of positive charges in the nucleus, that 2. And then the nitrogen has a subscript 7 on the left and a superscript 14. So the subscript 7 is the protons. So there's 9 protons. You can read it right off the equation. So I've got helium-2,4 plus nitrogen-7,14, and then arrow for a reaction goes to oxygen-8,17 plus hydrogen-1,1. And the bottom, the subscripts on the left, those are the charges in the nucleus. So you can see 2 plus 7 is 9, 8 plus 1 is 9. Charge is conserved. The top numbers stay the same too. Look, 4 and 14 is 18 to begin with. That's the number of nucleons. And then afterwards, it's 7 plus 1 is also 18. So nucleon number is also conserved in this nuclear reaction, and in fact, in all nuclear reactions. So that turns out to be a fundamental principle of physics, that the number of nucleons has to be conserved. That's that A, capital A, number of nucleons. And so you can see that built right into the way we write the equation. These equations, in a reaction like this, you can see how the mass has changed, just like we did in the other reactions. So you can calculate how much mass is on the left, the reactants, the initial mass, and then like how much mass is on the right, the products, the final mass. And the Q, the so-called capital Q of the reaction, is defined to be the energy difference m initial c squared minus m final c squared. And then sometimes we write that as equal to m loss c squared, how much mass was lost in the reaction, assuming the mass afterwards is left, which would be what happens if it's exothermic, if it's going to release energy. So that's called the Q of the reaction, m initial c squared minus m final c squared. Can calculate that for this particular reaction, and you'd have to look up these particular atoms in the table. So the mass loss is, so here's helium-2,4. I looked that up in the table. It's 4.002603 U, the mass unit U. And then I'm adding the nitrogen, which is 14.003074 U. That's the initial mass, that sum. And then I'm going to subtract the sum of the oxygen, which is 16.9999132 U, plus 1.007825 U. So those would all be tabulated values. And in this case, you get, well, in this case, you get a negative number, negative 0.001280. So the mass loss is really a gain in this case. The mass didn't actually go down. So this wouldn't happen, spontaneously. You'd have to do something like shoot these at each other with a very high kinetic energy, so that they had some kinetic energy to go into the reaction, right? So they need more energy than what's just available from the mass. This is not exothermic, or we call it endothermic. These reactions don't usually happen just in everyday life because these are big nuclei that repel each other with all their protons. So they would have to be moving towards each other pretty fast in order to get close enough to undergo this nuclear reaction. So either you'd have to, well, nuclear physicists will shoot them at each other in particle accelerators, and then they get close enough to fuse, and then they can detect the end products. Or you could put them in a container and heat it up to really high temperature. That will get them moving fast. But that's often problematic because your container will melt at very high temperatures. And inside things like stars, these sorts of things can happen because then you don't have to have a container. So sometimes these sort of nuclear reactions occur in different astrophysical phenomena, not necessarily just on the surface of the Earth, unless you shoot them at each other in a particle accelerator. So the Q of this reaction, it's a mass loss times c squared. And the mass loss we calculated as 0.001280 U, but negative. So the Q comes out negative. And you could just multiply by c squared and you'd get an energy. If you put everything in SI units, you'd get energy in joules. But nuclear physicists like energy units of MeV, mega electron volts. So you could first make this in joules and then convert it to mega electron volts by a conversion factor. But as a shortcut, it's convenient to do this. Look, if you take this mass loss minus 0.001280 U and multiply by c squared, that mc squared, then instead of putting in c in SI units, you can just think of c as its own speed unit and just say, okay, well, it's u, I got a u in there from the mass, times c squared, so that's just uc squared. And that itself is an energy unit, a non-SI energy unit, uc squared. And then a conversion factor to another non-SI energy unit, the MeV, is 931.5 MeV per 1 uc squared. So we can go, instead of going through joules, which would work too, it's just more tedious, we can go directly from uc squared as an energy unit to MeV. So in this case, multiplying that mass loss by 931.5 gives you minus 1.192 MeV. So that amount of energy would need to be supplied to make this reaction go. Usually comes from the kinetic energy of the participants. So there are tons of nuclear reactions like this that can be induced, but you have to get them going fast enough to overcome their Coulomb repulsion. And sometimes you have to actually supply energy for the reaction to go. This is endothermic. There's a quantity called binding energy for a nucleus. And binding energy is how much energy is associated with the nucleons being bound into that nucleus. So you calculate it like this. So we call if you take the masses of all the pieces that go into a nucleus. So take a nucleus like I don't know, like carbon 14. So then that has what is it? 6 protons and 8 neutrons. So what you do is you would take the mass of a free neutron multiplied by 8. That's n, the capital N, the neutron number. And then plus the mass of a hydrogen atom and multiply by 6, that's Z. So that's the sum of the masses of all the constituents. Because if you do that for if you use hydrogen instead of a proton, then that includes the right number of electrons automatically. So then that's the whole atom. Or that's the sum of the masses of all the pieces that went into making that atom. And if you subtract from that the neutral atom mass, say it's carbon 14, then the difference you get is called the mass defect. And in general, it will be less because there's more potential energy when you take the particles apart than when they are together. So that difference between the mass of the whole and the sum of the masses of the parts is called the mass defect. And then the neutral atom mass has all the electrons too. So we're really just subtracting out the electrons. Here's an example. If you do helium 2,4, so helium with 2 protons and 2 neutrons, and so then you do it. So the mass defect would be 2 times the mass of a hydrogen atom. It's 1.007825 U. Includes 2 electrons, plus 2 free neutrons, 2 times 1.008665 U, and then subtract the entire mass of a neutral helium atom, which is 4.002603 from the tables. And you get plus 0.030377 U. That's the mass defect for that atom. And then if you multiply by c squared, then that gives you the what we call the binding energy of that nucleus. And that's equal to what it would take to separate that nucleus into its individual pieces. You'd have to put in this much energy. So for a helium atom, it would cost you 0.03 U to take apart the 4 nucleons. And that's in mass units. You multiply by c squared to get in energy units. And here you could do that shortcut again. You could say, well, it's 0.03 U multiplied by c squared, and that's 0.030377 U c squared, and you can convert that to MeV using that conversion factor from the last slide, and that's 28.296 MeV. So that's the binding energy of helium. Now, you might wonder, like, who cares? Okay. So here's where it gets interesting. So this idea of binding energy. That's the binding energy of this whole nucleus. But it's interesting to think about what is the binding energy of per nucleon. What's it like to be a nucleon in a helium atom versus being a nucleon in a carbon atom? So then we'd need the binding energy per, there's 4 of these nucleons, right, in the helium. So this is the energy of the 4 of them. But the binding energy per nucleon, we divide by 4, divide by A, the mass number. And in this case of helium, that would give us, divide by 28 by 4, you get 7.1 MeV. So that's the energy per nucleon in helium. So that's an indication of how tightly bound that each nucleon is when it's in a helium atom. And we can calculate this for lots of different nuclei. We could calculate it for gold, we could calculate it for uranium, for carbon, for iron, and see which ones have a bigger binding energy, which have a smaller binding energy. And that's going to tell us something about how stable the nucleons are when they live in the different atoms.